This talk is not going to be political at all. It's just this is history and a little bit of physics. And this is not physics from hell. This is just fourth grade physics that we all had but kind of forgot. And again, it's history. And the history of the atomic bombs, there were actually two of them that we dropped on Japan. One was uranium-based, the other was plutonium-based. This took place in August of 1945. And this is the history leading up to getting these bombs designed, built, and delivered. And it is an incredible story. It is enormous. The number of people, the number of projects, the number of things that had to happen to make this happen. I'm going to leave a lot of stuff out because there's just no way you can cover it all. These are the books that I used for this. Richard Roth's book, The Making the Atomic Bomb. You can see how wrecked this thing is from all the times that I've gone through it. And I found this one made in Hanford. This is Hanford, Washington is where they made the plutonium and separated the plutonium from the other stuff so we could have the plutonium bomb. Now, we're going to start in 1938. And in 1938, it is impossible to split the uranium atom. In 1932, all right, this is some of the physics. This is all stuff we've had. The electron was discovered by J.J. Thomson in 1897. The proton was discovered by Rutherford in 1920. The neutron has no charge, and it was discovered by James Chadwick in 1932. Since Chadwick has discovered the neutron, they've been firing this dude at anything that they can to see what will pop off. Groups all over the world are doing this. And for this talk, we're only going to be talking about neutrons and protons today. And here's a little bit of numbers. The mass of the neutron, the mass of the proton, and the mass of the electron. Now, I remember taking a physics class more than 40 years ago, and I saw these numbers, and I thought, wow, look at this. The proton is positively charged, the electron is negatively charged. And look how, if you add the mass of the proton and the electron, they're about the same as a neutron. And if you take the positively charged proton and you cram into it the negatively charged electron, well, you have a neutron. I wondered about this more than 40 years ago. I never was able to do anything with it, but I wondered about that. The neutron is zipping into all these atoms because it has no charge, and it just flies in there like a little BB to knock stuff off, and then the researchers try to determine what they have left. This is a periodic table, and this is important. This is a concept. An element is determined by how many protons it has. That's it. It isn't any more complicated than that. This is barium. It has 56 protons. If an atom has 56 protons, it is barium, period. Down here we have uranium. It has 92 protons. Neptunium, it has 93 protons. Plutonium has 94 protons. And here's krypton. Krypton has 36 protons. So anyway, the point I'm trying to make, an element is determined by how many protons it has. Okay, this is going to be important later. All right, you've all heard the word isotope, and I'm going to explain this right now very quickly. If you have 92 protons, you are uranium. But you can have a different number of neutrons. So U-238 and U-235, they both have 92 protons. U-235 has 143 neutrons, and U-238 has 146 neutrons. And so there's where the 235 comes from. If you add these two numbers together, it's 235, and the 238 comes from these two numbers. These are isotopes. They are the same, but they are still different. They're the same element, but they have a different number of neutrons. Barium has got a whole bunch of different atoms that have different numbers of neutrons, and typically all of the elements are that way. Here's carbon-12. This is the one that we all know and love. It has 6 protons, 6 neutrons. Carbon-13, 6 protons, 7 neutrons. Now these are stable. These have been around since the beginning of time. They will be around till the end of time. But carbon-14, it is not stable. And it is not stable because it has too many neutrons. This is where radioactivity comes from. Again, an atom can have a certain number of protons and be stable. But if you have too many neutrons, you become unstable. And when an atom becomes unstable, it starts firing things off, and this is radioactivity. And some radioactivity is no big deal. Alpha particles coming off, they just bounce off the skin. If you hold up a piece of paper, they just bounce off the paper. No big deal. Some of the radioactivity is deadly, and I do mean deadly. Gamma rays, if you're in a room where gamma rays are given off, they will puree you, and you will not be able to get through the door before you are dead. So that is where radioactivity comes from. Too many neutrons. I hope there are no particle physicists in here who are saying, Bob, you're full of... But that's the way it is, yes. All right, it's 1938. It is impossible to split the uranium atom. And we're going to start showing the people in this. This is Lise Meitner, and this is Otto Hahn. They were in Berlin. They've worked together for 30 years. She's a world-class physicist. He's a world-class chemist. He does the chemistry. She does the physics. Lise Meitner. Otto Frisch is her nephew. You just met Otto Hahn, and then there's another guy. His name is Strassman. He's going to work with Hahn. Now, one of the sad parts of World War II is how badly the Jews were treated, and it is tragic, and it breaks your heart. And Lise Meitner is Jewish, and she has stayed in Germany too long. Albert Einstein left Germany for the last time in 1932 because he saw the handwriting on the wall. He saw what was coming. Hans Bethe left in 1935. Lise Meitner, it is 1938, and she has stayed too long. It is really getting tough to get out of Germany if you're Jewish. She wants to go to Sweden to work at a university to get out of Germany, otherwise she's going to be killed. And in July 13th, 1938, she's trying to cross over into Holland on her way to Sweden. And there are 5 guards there. And she hands the guard her passport. It expired 10 years ago. And if he points that way, she goes to Sweden. If he points that way, she goes to the camps in death. And I cannot imagine being in that circumstance. And he points that way. Who knows why? Just a nice guy. And she goes to Sweden, and now she's doing research in Sweden. This is July of 1938. Her nephew, Otto Frisch, he has left Germany, and he is in Denmark doing research there. Now, when they're finding a neutron at uranium, think of it as a sculptor with a hammer and a chisel, and they're just knocking little pieces off, and they're trying to figure out what those pieces are. And maybe if they knock the right stuff off, they can go to the next element in the periodic table, knock a proton off, and make neptunium, which hasn't been discovered yet. Or they can knock something off and it'll be some other element. So this is the kind of research you're doing, just knocking little bits and pieces off of uranium. This is Otto Hahn's work table. It's been recreated. And this is where he is firing neutrons at uranium. And one of the things they've discovered is that you can have fast neutrons and you can have slow neutrons. And slow neutrons work better to fission, to split uranium. And right here, you can see the paraffin. And they're using paraffin to slow the neutrons down. This is a moderator. Over at Fermi and all the other nuclear power plants in the United States, They use water to slow the neutrons down. Later on, when we start building nuclear reactors, we're going to use graphite to slow the neutrons down. It's a moderator. It slows the neutrons down. Again, this is paraffin, and this is what he's using to slow this down. Now, Hahn is a world-class chemist, and he's firing neutrons at the uranium, and then they're looking at, what do we have? And he finds barium. And this makes no sense at all. Where did the barium come from? It makes no sense. And he's thinking contamination, but he's so careful that it can't be contamination. And he doesn't understand the physics of this, so he writes this long letter to Lise Meitner in Sweden about what he has found. And Otto Frisch has come to Sweden to spend Christmas with his aunt. She shows him the letter from Hahn, and they start talking about it. This is something brand new. And the day before Christmas, in 1938, the 60-year-old aunt and her 34-year-old nephew go for a walk. Meitner loves to walk. It is nothing for her to walk 10 miles in a day. Think of it. Sweden in December, cold, snow on the ground. Aunt walking briskly, nephew on cross-country skis, and they're talking about the letter. And as they walk, they're talking about this, and they talk, and they talk, and pretty soon, the ideas start to form. They start to coalesce. They sit on a log in the woods of Sweden in the snow. She pulls paper and pencil from her purse, and they start to do the things world-class physicists do. They start with diagrams to see what is the uranium atom doing as it's getting hit with the neutrons, trying to visualize this, and then the equations begin. Frisch says, I remember that I immediately at that instant thought of the fact that electric charge diminishes surface tension. The liquid drop is held together by surface tension, the nucleus of the analogous strong force. And so I promptly started to work out how much the surface tension of a nucleus would be reduced. I don't know where we got all the numbers from, but I think I must have had a certain feeling for the binding energies and could make an estimate of the surface tension. Of course, we knew the charge and the size reasonably well. And so as an order of magnitude, the result was that at a charge, number of protons of approximately 100, the surface tension of the nucleus disappears. And what he's saying is, if you have an element with 100 protons, it's unstable. It will not hold together because the binding energy that holds the nucleus together, the protons are all positively charged. They want to push each other apart. The binding energy is holding them together. And he says if you have 100 protons, those two things cancel out and the atom is just going to fall to pieces. All right, they're seeing this sitting on a log in the snow in Sweden. They had discovered the reason no element beyond uranium exists naturally in the world. The two forces working against each other in the nucleus eventually can't cancel each other out. And this is what they see. You have U-235. It has 143 neutrons, 92 protons, and its atomic mass is 235. 235 protons plus neutrons. And if you add a neutron, now you have U-236. You have 144 neutrons. You still have the same number of protons. And this splits the uranium atom. And I want to show this because this is important. And this is a really, really cheesy way to do something, but I decided I was going to do this. This is my uranium atom. Yes, I know. I spared no expense in this. This is a uranium atom, all right? And when you see the protons in here, this stuff, this is the binding energy. This is holding everything together, holding the protons together. And as the neutron comes zipping in here and hits it, it starts to go through all kinds of gyrations, and then, if I can get it to work out right, it splits into two new atoms. The uranium atom is gone. It is gone forever. And now you have two brand new atoms. And now the question is, what are these two new atoms? And the solution is, how many protons do they have? In this case, this new atom has 56 protons. So if it's 56 protons, it's barium. Like I said, the uranium atom is gone, and now we have barium. And if we have 56 protons here, and we had 92 to begin with, 92 minus 56 is 36. And the other one then, you just go to the periodic table and you find the atom with 36 protons, and it's krypton. Krypton is a gas. It's gone. That's the reason he only found barium. All right, so you have barium and krypton got created by the splitting of the uranium atom. And whatever you're going to get, the protons in those two new atoms are going to have to add up to 92. And if you look across the periodic table, if you look across the middle of the periodic table, you have all of these atoms with 56, 57, 58, 59, 60 protons. You don't know what you're going to get. You could get an atom 2 with 46 protons. 46 and 46 is 92. You could get 50 protons and 42 protons. But you don't know what you're going to get ahead of time. All right, that's what happens when you split an uranium atom. Now think about this. It's a day before Christmas in 1938. It is impossible to split the uranium atom. And in the woods, in the snow, sitting on a log, two people show that you can split the uranium atom. It is a singular event in the history of physics. I showed here, here's barium and here's krypton. And the magic of this is that it also gives off 3 neutrons. Gotta clean up my hands. The 3 neutrons that this gives off, these are free neutrons. They can boogie anywhere. This is what makes a chain reaction possible, because now you have free neutrons. And I drew a thing on the board to try to show this, because this is what takes place in a nuclear power plant. This is a chain reaction, and here's my atom that I was holding in my hand. A neutron hits it, and it gives off 3 neutrons. Now, each neutron goes off and splits another U-235. 3 of them, and then each one of these gives off 3. Sometimes it gives off 3, sometimes it gives off 2. But this gives off 3. This goes off and splits 3 U-235s. This one splits 3 2 U-235s, and this one goes off and splits 2 of them. And then the next generation, you have even more, and the next generation you have even more. I mean, it doesn't take a lot of imagination to realize if you take this out 10 or 12 generations, you're going to have a lot of split uranium. In the 10 millionths of a second that a bomb takes to explode, a nuclear bomb takes to explode, you're going to have about 10 to the 27th fissions. And each one of those, it may only be a skosh, but when you have 10 to the 27 of them, that's where the power comes from. 10 to the 27 of these fissions. Big number, all right? That's the power of the atom put to some kind of use. Now, Lise Meitner says if you really do form 2 such fragments, they would be pushed apart at about 1/3 the speed of light. She's doing all these calculations in her head because she doesn't have a laptop, she doesn't have a bank of computers, she doesn't have Google. All these numbers are coming out of her head. She's making the calculations and doing this stuff. And I am completely impressed sitting on a log in the woods of Sweden, and you're doing this work that no one has ever thought before, no one has ever done before. Now, she calculates that the uranium and this neutron, after they fission, you're going to be about 1/5 of a proton less mass. So this side of the equation is, I got it wrong, I say a third, it's supposed to be a fifth. A proton less mass, and this is about 200 MeV. She plugs this stuff into Einstein's E equals mc squared equation and calculates this is the amount of energy. And again, she's doing this in her head. Okay? So this is where the energy comes from, the 200 MeV for each one of these fissions. Now, when the word gets out that this has happened, every university in the United States starts doing this experiment. And a lot of these guys are doing it in less than 24 hours. So it took Han years to get to the point where he could get here, and as soon as he does it, poof, everybody's doing it. And it became a big deal. It was like a parlor trick. People were doing this in their spare time. Now, Otto Frisch, Lise Meitner's nephew, he sees Niels Bohr on January 3rd, 1939, and he explains the fission of uranium. And Bohr hits himself on his forehead with his hand and says, "Of course, what fools we have been. It has to be that way." Like I said, the day before Christmas, it was impossible to split the uranium atom, and now it's obvious that it can be split. And I missed something here. Oh, there it is. Frisch is doing this experiment, and everyone who walks past, he's dragging them down there to show the experiment. And he has a biologist who couldn't care less, but he's seeing the experiment. And Frisch says to him, in biology, when a bacterium splits, what is that called? And the biologist says, fission. And that's where the word fission comes from, to explain uranium atom or a plutonium atom when they split into pieces. That's where fission comes from. Now, I want to show this. Lise Meitner never won the Nobel Prize. And I'm not going to go into why. It's very complicated and it's sad. Oh, where'd you go? Where'd you go? Where'd you go? She died in 1968, and in the 1980s, researchers in Germany created a new element. And they shipped this stuff off, and the sanctioning board for elements, when you create an element, you get to name it, and they submitted a name, and in 1992, the sanctioning board okayed that name, and the name they submitted and the name they okayed was Meitnerium. They named it after Lise Meitner. And if I can find my mouse. There it is right there. So this element was named after Lise Meitner. It's element 109. Okay? And now you know why that's my favorite element.
Now, quick question.
Okay?
What made those early scientists think about uranium as the element to use for trying to split?
Because they could get more stuff off of it. It was easier to work with. They were shooting neutrons at everything. Every element they could find, they were shooting neutrons at it to see what they could find. This is new territory. This has never been done before. Now, 2 weeks later, after Meitner and Frisch do their work, Luis Alvarez, he will win the Nobel Prize, is reading a newspaper at Berkeley while he's getting a haircut. He reads in the newspaper that Germany has split the uranium atom. He jumps up in the barber chair and runs over to the radiation lab. He finds his graduate student, shows him the newspaper, and the next day, his graduate student duplicates what Han did in Germany. And Alvarez says, I remember telling Robert Oppenheimer that we were going to look for ionization pulses from fission, and he said, that's impossible. Now realize, 1938, it's impossible to split uranium. And one by one, people are saying, oh wait, it is possible. Cool, and gave a lot of theoretical reasons why fission wouldn't really happen. When inviting him over to look at the oscilloscope later, when he saw the big pulses, those big 200 MeV pulses, I would say in less than 15 minutes, Robert had decided that this was indeed a real effect, and he had decided that some neutrons would probably boil off in the reaction, and that you could make bombs and generate power all inside of a few minutes. It was amazing to see how rapidly his mind worked, and he came to the right conclusion. When Abelson is doing these reactions he's getting tellurium and zirconium. Remember I said you don't know what you're going to get? That it could be any of the elements in the periodic table in the middle part. It's the same reaction, and it gave off 3 neutrons to show the chain reaction. Now, let's go back to 1934. Fermi and his team have been firing at neutrons at anything they can find. And they're the ones who determined that slow neutrons work better than fast neutrons. They actually had wood on their tables, and the wood was slowing the neutrons down. And they tried water, and they found that that worked too, and then they discovered paraffin. Paraffin worked also. And they thought, again, this is 1934, they thought they were knocking little bits and pieces off of uranium. And they wrote this up, and this is what Fermi wins the Nobel Prize for, only to find out later that he had made some gigantic mistakes. And this is Ida Natick. She's a chemist. She was nominated 3 times for the Nobel Prize in Chemistry. And she writes a letter to Fermi and saying, you're looking in the wrong place. You need to look in the middle of the periodic table for your results from when you're splitting, when you're hitting the uranium atom. Fermi doesn't think it's possible to split the uranium atom, but she sees it. She knows that this is possible. She can't prove it because she's not a theoretician, she's a chemist. And like I said, she wrote a letter to Fermi, and she said, you need to look at the products, you need to look at the pulses and stuff of the atoms from the middle part of the periodic table. You're misreading what you're seeing. And Fermi does the calculation, but he does not see how uranium can be split. He was using a reference number that had been calculated by one of his team, and the number was wrong. And when he plugged that into the equation, it showed that uranium could not be split. It was a mistake. And on their oscilloscope, they're seeing these big pulses, these big 200 MeV pulses, and it's starting to piss them off because they're obscuring the data they're looking for. So these 200 MeV pulses are showing that they're splitting uranium. This is what Lise Meitner calculated on the log in Sweden. And so what they do is they cover it, uranium, with aluminum foil, and that blots out the 200 MeV pulses. They discovered the splitting of the uranium atom, but they didn't know it, and they lost the discovery. And it's part of history now. All right, I've already gone through what radioactivity is. Radioactivity is when you have too many neutrons. The letter. There are a bunch of guys from Hungary. There's John von Neumann, there's Leo Szilard, there's Edward Teller, and there's Eugene Wigner, just a few who are coming from Hungary to the United States. They are world-class physicists. Wigner will win a Nobel Prize. John von Neumann was a mathematical genius. He was incredible. But they've all come to the United States, and their families are being slaughtered in Europe. The Nazis are getting them. They're all Jewish. Their families are going to the concentration camps, and they're all being slaughtered. And they realize that if Hitler can get an atomic bomb, he will use it. So these people from Hungary that I just mentioned, they say, we've got to warn the President of the United States that the Germans can make a bomb. They're way ahead of us in this, and if they could make a bomb, they're going to. So they find Einstein. Einstein is on the left. This is Leo Szilard. He will show up again later. Szilard knows Einstein. and they find him. Einstein is on Long Island. He's rented a house there. He's sailing. And on a Sunday, July 16th, 1939, they go to Einstein's house and they write a letter to Roosevelt. And they want Einstein to sign it, warning Roosevelt that the Germans are ahead and that if they can make an atomic bomb, they will, and we need to do the same thing. We need to beat them to the punch. And the letter is delivered in October 11th, 1939 to Roosevelt, and he forms Uranium Committee to look into what we could do with the splitting of the atom. Now, what's interesting about this, July 16th, 1939, the Trinity test, when they fired the first atomic bomb. Trinity is south of Albuquerque in New Mexico. It's a big piece of desert. And the Trinity test took place July 16th, 1945. So 6 years. In 6 years, you go from a theory that's not possible to bombs. And to get all this stuff built and get all this stuff organized and get all these things done in 6 years is absolutely incredible. Now, in 1939, 1940, and part of 1941, there are all kinds of reactions taking place. And the problem they're running into is there's a depression, there isn't a lot of money, the universities can afford hundreds of dollars for tests, but they cannot afford millions of dollars for these experiments. And they are trying to prove that a chain reaction will work. And they really can't. They don't have the equipment, and they don't have the money to pull it off. And what they find out by the middle of 1941 is that U-238 will not work for a bomb. Slow neutron fission is for power plants, not for bombs. This is what the nuclear reactors use. Fast neutron fission is for bombs. U-238 will not work out for a bomb or for fission for a bomb. U-235 is what they need for slow neutron fission for power plants. And then they're going to show that if you want to make a bomb, you have to have U-235. So these are some of the things that they've discovered in these intervening years. Now here is the problem. For every 139 atoms of uranium you have, one is U-235 and 138 are U-238. How do you separate one atom of U-235 from 138 atoms of U-238? They're chemically identical. There's 3 mass units difference between these two. How are you going to do that? U-238 is not going to work for a bomb. You've got to have 235. How do you split them? How do you split out the U-235 from this? Okay, the development of plutonium. Plutonium is what's going to go into the Fatman bomb. Now, at the point 1938, there are no atoms on the periodic table above uranium. They do not exist. And plutonium is going to have to be discovered and created, and it's going to come from beta minus decay. And in January 1939, Niels Bohr and John Wheeler determined that element 94 plutonium is possible, and that it would be an excellent candidate for fission. It's never been seen, it's never been created, but they think it can be. This is a ring of plutonium. This is what it looks like. And it's a ring because you do not want to create a sphere of this stuff. Because if you create a sphere, it will start to fission. So you want to create something where the neutrons can get away as easily as possible without creating a lot of mayhem on its way. But that's what plutonium looks like. This is Glenn Seaborg. He is one sharp dude. He has an element named after him. So uranium was named after Uranus, Neptune is named after Neptune, plutonium is named after Pluto. Its symbol is Pu. Seaborg did not want it to be confused with platinum. If you create an atom, you get to name it. Seaborg is in 1940 producing neptunium and studying its chemistry. He thinks maybe he has produced some plutonium. Now, here's some physics. Physics we all know and love. This is beta minus decay. And beta minus decay is where a neutron is converted to a proton. Okay, remember up above I said maybe a proton and an electron, if you cram them together, become a neutron? So what they're saying is you take a neutron and you convert that dude to a proton, it's going to give off an electron and an antineutrino. Okay? So what we're going to have is two beta minus decays. Can you all see that? This is just some arithmetic, okay? We have U-238, and it gets hit with a neutron, and now it becomes U-239. It still has 92 protons, but now it has one more neutron. And what it's going to do is it's going to go through a beta minus decay, and one of these neutrons is going to convert to a proton, give off an electron and an antineutrino. Now, because now you have 93 protons, now you have neptunium, because it has 93 protons. And neptunium then beta decays with a half-life of 2.3 days. One of its neutrons gets converted to a proton, and now we have an element with 94 protons, and this is plutonium. This is plutonium-239. Now, this is U-238. It won't work in a bomb, but we can use U-238 to make plutonium. And if you have a nuclear reactor like over Fermi or Browns Ferry or these places, there's a lot of U-238 in there, in the fuel. And this process is happening all the time. The plutonium is being created inside these nuclear reactors, and then the plutonium gets hit with a neutron, and it fissions, okay, and gives off energy. And then it has fission products and becomes something else. About 1/3 of the power in a nuclear reactor is from this reaction, right here, okay? So U-238 is important in a nuclear power plant, only it's not fissioning, it's transforming into plutonium, which gets fission. All right? So this is when U-238 captures one neutron, and if U-238 captures two slow neutrons, now we have plutonium-240. And this dude is going to pop its ugly head up later on when we get into the bombs. Now, one of the immediate questions is, what is a half-life? And so I'm going to try to show it here. And we have a scenario, we have 1,000 atoms of neptunium, and these are going to be converted via beta decay into plutonium. So we start off with 1,000 atoms of neptunium, and in a half-life of 2.356 days, half of this is converted into 500 atoms of plutonium. That's what it means by half-life. In each one of these half-life time periods, 2.3 days, half of whatever you have is going to be converted into something else. Okay? We start off with 1,000, so in 2.3 days, half of it's gone, and now we have 500 plutonium atoms. And in the next 2.3 days, half of whatever we have here is going to be converted, is going to be lost and converted into 250 atoms of plutonium, and so on, down the line. Now, there are only two things that you have to realize from this. In the first half-life, 2.3 days, and everything that decays has a different half-life. Some half-lives are less than a second. Some half-lives are thousands of years. The first half-life, half of what you have is gone. That's a lot. Okay? And we're going to see this later on, how this appears. And if you have 10 half-lives down here, essentially everything you had is gone. 10 or 11 half-lives. So the first half-life, half is gone, and by the time you have 10 or 11 or 12 half-lives, it's all gone. It's all decayed into something else. So you can see a James Bond movie where he's got some deadly radioactive product out here that has a half-life of a second. And the damsel in distress is over on the other side of the room. And all he has to do is wait 11 seconds and it's all gone. It's all decayed. Okay? That's a half-life. Segre and Seaboard bombard 10 grams of solid uranium for 6 hours in a 6-liter cyclotron at Berkeley. 1 kilogram of the uranium they calculated suitably irradiated should produce about 6 micrograms. This is essentially a millionth of a gram from neptunium after allowing time for beta decay. Now begins the process of separating the plutonium. You can create plutonium. You have a nuclear reactor and you can create plutonium, and the cool thing is plutonium is different chemically from everything else. So you can use chemical separation to pull the plutonium out. All right? So the guys who are in charge of this process of trying to make an atomic bomb in the United States, they see the nightmare of separating U-235 from U-238, but they see this as cool because we can do it with chemistry. It'll be easy. How hard can it be? And so from 1.2 kilograms of uranium hexafluoride, they have separated less than a millionth of a gram of pure neptunium. They perform a fission test, and it gives a strong indication that plutonium undergoes fission with slow neutrons, and they find that the cross-section of plutonium is 1.7 times that of U-235. It wants to fission. To make plutonium, they need to have a chain reaction. You've got to build a reactor with all these neutrons flying all over the place so that the uranium can capture one and go through the beta decays to make plutonium. Without a nuclear reactor, this is not going to happen. They're starting to build the reactors. And the first reactor is at Columbia University, September 1941, and it has a K of 0.87. If the K is 1, your neutron stable. If it's less than 1, eventually all the neutrons disappear. They're gone, and the reaction stops. If the K is greater than 1, you are producing more neutrons than you're using, and this is a chain reaction. This is what you have to have. It has to be more than 1. They're using graphite as a moderator to slow the neutrons down. And one of the problems they run into is that as they're getting the graphite, it has boron in it. It just naturally does. And the boron is sucking up the neutrons, and it is really screwing up their chance to make a reaction because the boron is sucking up the neutrons as fast as they can be generated. So they have got to produce graphite that doesn't have boron in it. And it becomes Thursday, August 20th, 1942 was the first time that plutonium had been seen by the eye of man. And this is through a microscope because they just have a skosh of this stuff. Now, the letter to Roosevelt created the Uranium Committee, and the people they put on the Uranium Committee were not capable of dealing with this. And other people eventually started working their way into this, and they became in charge, and they actually knew what they were doing. When you have a project as big as this, you have to have people in charge who actually know what they're doing. I mean, really know what they're doing. And you have to have the physicists and the chemists and all these other really, really smart people who do their thing. And then you have to have people who can build the facilities to get all this stuff done. It isn't just a bunch of physicists stirring a vat. You learn very quickly you need all of these groups. November 27th, 1941, the final group, meets with Roosevelt to talk about the bomb. No one knows what they said, but you kind of get the idea they got their marching orders. I mean, November 27th, 1941, we're coming close to
Pearl Harbor.
Yeah. Now it's December 6th, 1941. Does anyone see the irony of that? This is December 6th. 77 years ago, 3 guys meet at the Cosmo Club in Washington, D.C. to have lunch. A guy named McConnett, Bush, and Compton. Compton's a Nobel Prize winner. The other 2 were presidents of the university. They were all the perfect 3 to head this up. And they're deciding, how are we going to build the bombs? What are we going to do? They decide we're going to separate U-235 from U-238, and by either gaseous diffusion or electromagnetic separation. And Compton says we cannot leave plutonium out, and he starts arguing for it. They don't want to do plutonium. It's dangerous. It's making all this stuff that's really nasty, and this is nasty stuff. We don't want to do this. But Compton says, look, what if the other 2 fail? We've got to do plutonium. So finally the other 2 say, all right, you think plutonium is so important? You do it. Be careful what you wish for. So now Compton's in charge of making plutonium. This is electromagnetic separation. And Lawrence is working, he starts in late 1941 to use electromagnetic separation to separate U-235 from U-238. And this is unbelievable. In this little pot, you have uranium, and you turn it into a gas, and you give it charged particles. And on this side of this, you have a magnetic field, and on the other side of this, you have a magnetic field. And because these ions, these atoms, are in a magnetic field, they go through an arc. And because U-235 is lighter than U-238, it goes on this narrow arc, and U-238, because it's a little heavier, goes on this bigger arc. And down here you have these little buckets collecting the U-235, and you're collecting the U-238. This is electromagnetic separation. You need big magnets and some process to do this, and all this has to be done in a vacuum. This is over a 4-foot area. Lawrence at Berkeley has got a cyclotron, and he decides to convert it to create electromagnetic separation. And by running it continuously for a month, he's produced a partially separated 100 micrograms of U-235. Now this is millionths of an inch, or millionths of a gram. This was several hundred million times less than the 100 kilograms Oppenheimer originally estimated would be necessary to make a bomb. Lawrence has committed his time to winning the war. He committed his beautiful new 184-inch cyclotron. He had a D-shaped mass spectrometer tanks installed between the pole faces of a 4,500-ton magnet. Making this new instrument work through the spring and summer of 1942 solved the most difficult design problems. He had 168 PhDs working on this. These guys were working 24 hours a day, 7 days a week to make this happen. And these became known as calutrons. And this is another tron from the University of California. They were also called racetracks and alpha and beta. To separate 100 grams, about 4 ounces of U-235 from day, Lawrence estimated in the summer of 1942 would require 2,000 4-foot calutron tanks set among thousands of tons of magnets. If a bomb needed 330 kilograms, 66 pounds of U-235, 2,000 such calutrons could enrich it material enough for one bomb core every 300 days. That assumed the system worked reliably, which it hadn't so far. In 1942, electromagnetic separation still looked so much better than either plutonium or gaseous diffusion. The group in charge are about to decide that electromagnetic separation should be the only process to use. Lawrence was self-confident, but he wasn't foolhardy. He insisted that all three be used. Okay. That's electromagnetic separation. This is gaseous diffusion. Gaseous diffusion is where you have a membrane with little tiny holes in it. And you have uranium hexafluoride as a gas, and you put it under pressure, and if you have these little tiny holes, the U-235 being a skosh smaller than U-238 are more probabilistically thought to go through the holes first than the U-238. This is it. You're making this sheet with holes in it, and you're just blowing this stuff at it. And the U-235, when it comes out the other side, should be a skosh more dense than what you had on the other side. And then you do this again. You blow it through another membrane, and then you blow it through another membrane, you blow it through another membrane, and another membrane. 4,000 of these cascades. And by the time you get done, you should be about 90% U-235. This is enormous. Enormous amounts of power. This membrane is made in the shape of a tube, so the pressure would blow it through all of the tube and then go to the next one. The U-238 would work its way down, the U-235 would work its way up the food chain. That was the plan. That was gaseous diffusion. So those are our three processes. We have gaseous diffusion, we have electromagnetic separation, and we have plutonium. And they're going to make all three happen so that they can try to make something work to make a bomb. And Leslie Groves, U.S. Army, he's a general now, is put in charge of developing and creating atomic bombs on September 17, 1942. He has just finished building the Pentagon. Groves will create three major locations tasked with creating an atomic bomb. Los Alamos, New Mexico. Major physics, design and build the bombs. This is purchased in December of 1942. Oak Ridge, Tennessee. Separate U-235 from U-238. This is purchased in September of 1942. Hanford, Washington. Create and isolate plutonium. This is purchased in January of 1943. The money is starting to flow.
So they use both processes in Oak Ridge?
Yes, yes. This is Robert Oppenheimer. He will head up Los Alamos. And this is Leslie Groves. He is the general who is in charge of getting this whole thing done. He is a hard charger. He is the one who's going to make the decisions and make this thing happen. This picture was taken at the Trinity test site. And there was a 100-foot tower there. And this is a few days after the explosion. And this is all that's left of the tower. The concrete footing is gone, and there's just some rebar left. And the rest of the tower has been vaporized. It is gone. But this is Oppenheimer, and this is Groves. Robert Oppenheimer was put in charge of the design team for the bombs of Los Alamos on October 15, 1942. He was 38 years old in 1942. Hans Bethe said that by then he had done massive scientific work. In the summer of 1942, Oppenheimer gathered together in Berkeley a small group of theoretical physicists. Their job was to try to determine if they could design atomic bombs. Bethe said, now Bethe will head up the theoretical division at Los Alamos. he will win the Nobel Prize. He is one sharp dude. Beta said, now I could see at first hand the tremendous intellectual power of Oppenheimer, who was the unquestioned leader of our group. He said, watching Oppenheimer at the blackboard with the chalk, taking the problem apart and putting it back together again, was breathtaking. All these other guys, they started, but they all got stuck. And Oppenheimer tore the problem to pieces and put it back together again. He was definitely the one they needed to do this. Now, the problem you have is you're going to have all these physicists working on an atomic bomb, lots and lots of secrets. So Groves says, we're going to have all these physicists, we want it to be a remote location. So they decided on New Mexico. This is the site where they're going to put the physicists. This is the Mesa. It's up on here, and you can say remote, as in way remote. And what's cool about this, in 1927, Oppenheimer leased a cabin in New Mexico, about 60 to 75 miles from this location. And the cabin was very primitive. You slept on the floor. This is 1927. There's no electricity. The cabin had horses, and it was nothing for him to fill up a sack with food, get on a horse, and be gone for a week. Sleep on the ground, just go out and see stuff. Oppenheimer had been here on his horse more than once. He'd been all over this area. He knew it. So when Groves was looking for a place that was remote and had some other things he needed, they go to the first place, Groves doesn't like it. They go to the next place, Groves doesn't like it. They go to the next place, Groves doesn't like it. And Oppenheimer says, I think I know the place, because he'd been there. And they drive up here, and this is the road. It's still there. This is how you get to Los Alamos today. And they drove back on here, and there's a boys' school here. There's a lodge for the boys to live in, and then there are houses for the faculty. And Groves loves it. This is it. This is where we need to be. And they will buy this, and this is where Los Alamos is built, is where Los Alamos will begin. Oak Ridge, Tennessee. The land that would become Oak Ridge was bought in September of 1942, 59,000 acres, 92 square miles of Appalachian semi-wilderness, rural poverty along the Clinch River in eastern Tennessee. In the winter of 42 and spring of 43, its contractors cut 55 miles of rail, 300 miles of paved roads and streets. The new town was called Oak Ridge. The entire reservation, fenced with barbed wire and controlled through 7 guarded gates, was named after a nearby Tennessee community, the Clinton Engineer Works. The new gates were closed to public access April 1st, 1943. Eventually, there are going to be 20,000 workers here, because they got to build all this stuff. Think about 1942, and you've got to feed and house 20,000 guys who are coming from all over. This is still a depression. They got nothing. They got wives, they got children. Here they come. You got to put them someplace to live. You got to have laundry facilities, cafeterias, schools, the whole shooting match. All this stuff has got to be built. Plus, electromagnetic separation and gaseous diffusion plants have got to be built. All this stuff has got to get done. This is a logistical nightmare. Groves bought the land for the Hanford site in January of 1943. He bought 500,000 acres. You're going to make plutonium, and you're going to have fission products that are really, really nasty. You want to have a big area, so in case something bad happens, you don't kill a lot of people. This is 59,000 acres. This is 500,000 acres. Eventually, there will be 45,000 workers here. Again, you got to feed these guys and house them, and they got wives and they got kids, and you got to do all this stuff. And this is rural. I mean, Hanford, Washington is nothing forever, and I cannot believe that they got all the lumber and nails and stuff in here to do all this stuff. They have to prove a chain reaction. You cannot have plutonium without a chain reaction. And Compton was put in charge of this. He's at the University of Chicago. He's got people on either coast, and traveling back and forth is a nightmare. He said, everybody's moving your facilities to the University of Chicago. Everybody's going to Chicago. And they have to build the reactors to prove a chain reaction. This is a football stadium at the University of Chicago. It's been disused for a long time. And what they're going to do is they are going to, underneath these stands, are double squash courts, and that's where they're going to build the first nuclear reactor. And between April 15th and November 13th, they have built 16 successive piles in the Stagg field to measure the purity of various shipments of graphite and uranium. When they were done, they would shape and finish 45,000 graphite blocks and drill 19,000 holes. The graphite is built like a big block, kind of in the shape of a sphere. They're all bricks, and they drilled holes, these big holes in the graphite, and they have spheres of uranium that they're dropping down into the graphite, and they're putting this whole thing together in this matrix, this configuration. And they got to calculate distances between the graphite, or between the uranium spheres, and how many to have vertically also. And they go through 16 of these processes to figure out how good the graphite is, and also to understand neutron activity. Fermi does not want something to take off and hurt a bunch of people. Create a chain reaction that just goes crazy and melts down and hurts a bunch of people. And in November of 1942, Groves has convinced DuPont to take over building and running the plutonium production piles under subcontract to Stone & Webster. DuPont admitted the possibility of regular production by 1945, limiting itself to a profit of $1. So they start the final reactor on Monday, November 16, 1942, and they're doing two 12-hour shifts to construct the first nuclear reactor. They call it CP1, Chicago Pile 1. The control rods are 13-foot strips of wood with a cadmium strip nailed to it. They spared no expense for safety. Leona Woods designed and built the devices that measured neutron activity. They recorded the neutron activity at the end of each shift. This is an artist's view of the first reactor. It is done December 1st, now it's December 2nd. They're going to start this thing up. And here it is. You can see the graphite blocks. It's kind of in the shape of a sphere. And all this lumber it's shaped like a sphere, so all this lumber's got to hold all this stuff up to keep this thing from falling down into a big pile of a mess. Here's the control rods. They only show one here, but there were more than one. And then all these people are up here in the balcony. They have machines here to measure neutron activity. These guys over here, you can see they have buckets with them. These are buckets of cadmium salts. If things start to get bad, you're going to throw the buckets on the reactor to stop the reaction from taking place. Again, they spared no expense for safety. And you can see this rope. A million years ago, I have a picture of this where you can see the guy with the axe. At the bottom of this rope, there's a guy with an axe, and if things start to go bad, his job is to take the axe and cut the rope, okay, to stop the reaction. I mean, how many safety features do you have to make everything work out right? So on the balcony, Leona Woods is there. She's right next to Fermi. I don't see her in this, which is kind of sad. And Crawford Greenwald, he is the chemical engineer from DuPont who's going to be in charge of building the reactors in Hanford, Washington, and extracting the plutonium. CP1 contains 700,000 pounds of graphite, 80,000 pounds of uranium oxide, 12,000 pounds of uranium metal. It cost about $1 million to produce and build. It would run no hotter than 1/2 watt. Fermi was a sharp dude, and he did not want this thing taking off. It has no cooling. If it gets too hot, it's just going to start melting down. And there's no shielding. I mean, if this thing takes off, it's going to get bad. So that's the reason he just wanted a skosh of power coming out of this thing. He just wanted to prove a chain reaction. That shows how smart Fermi was. The pile reached a K of 1.0006. The neutron intensity was doubling every 2 minutes. Left uncontrolled for an hour and a half, that rate of increase would have carried it to 1,000,000 kilowatts. Long before a so extreme a runaway, it would have killed everyone in the room and melted down. Fermi let it run for several minutes. At 3:53 p.m., Fermi had run the pile for 4.5 minutes at 1/2 watt. They had proved you could do a chain reaction. And now DuPont's problem is they just had a reactor running at 1/2 watt. They need to build reactors running at 250 million watts to make plutonium. And they still don't have a really good idea of how they're going to pull plutonium out of this mix when they pull it out of the reactor. Okay? So this is December 2nd, 1942. We are 3 years from Trinity. These are some of the people that worked on the reactor. This is Fermi, this is Leona Woods, and this is Leo Szilard. Remember, he was with Einstein. And just to put some history with this, the reactor was under the football stadium at the University of Chicago. The football stadium was torn down and buildings were built up around it. And this is a sculpture that was put there. It's essentially in the center where the reactor was to commemorate the world's first reactor. I took this picture, and I have a thing of bottled water here to give you a scale of the size of the sculpture. This is a library, and then to the left is a library, but this is where the reactor was built.
What's the sculpture supposed to be?
I have no idea. I'll let you. I thought, when I looked at it, I thought it looked like the fireball from Trinity. The first explosion, I thought it looked like the fireball. But that probably would offend the artist. He was probably more into peace than he was anything else. So now we can make plutonium, but now you got to pull the plutonium out of this mix. Now remember, you are irradiating uranium. We got fission products, right? The atoms that are creating this. Some of these are deadly. You can't just walk up to this and start stirring the vat and get the plutonium out, because if you do, you're not going to make it out the door before you're dead. They're going to have to work out a way to get the plutonium out of this mix. And in 1943, Greenwald says to Seaborg, "Can you guarantee me a yield of 50%? What he's saying is, of all the plutonium that's in this mix, can you pull out half of it? And Seaborg said, yes, I can. And Seaborg had created enough plutonium that you could barely see under a microscope, so he really wasn't sure. But being a sharp dude, he just said, yeah, we can. And there was a well-tested procedure that worked, but unfortunately produced such a corrosive mix that it tended to eat its way through anything containing it. And there was another method. They've got all these PhDs coming into Chicago to work on separating the plutonium from this other stuff. And again, we're talking about skoshas of plutonium. And these guys are killing themselves trying to come up with this. And one of the guys comes up with, it's sodium bismuth, I think. And he used some, it didn't work. He thought, oh, what the hell, I'll just use more. He used more and it worked. He was able to pull the plutonium out. And I'm not going to go into the chemistry of this because I don't understand it. And Seaborg was defining the method that defied theory. They didn't know why it worked, but it did. Now, obviously they do now, but this is, again, they just discovered plutonium. And like I said, they were working with a reactor. They had a reactor that was running at 1/2 watt, and now they're going to have a reactor at 250 million watts. and all this stuff has got to scale up. DuPont released the pilot design drawings on October 4th, 1943, and the engineers staked out reactor B on October 10th. Work began to lay the first of 390 tons of structural steel, 17,400 cubic yards of concrete, 50,000 concrete blocks, and 71,000 concrete bricks. Reactor B, there was no reactor A. Hanford's first reactor went critical a few minutes before midnight on Wednesday, September 20th, 1944. We're less than a year from Trinity. The reactor was silent except for the sound of river water being pumped through the reactor to carry off excess heat at a rate of 75,000 gallons per minute, going in at 50 degrees Fahrenheit, going out at 140 degrees Fahrenheit. This thing is designed to run at 250 megawatts. It goes up to 100 megawatts, but it won't go higher. And the people in the control room, the gauges have stopped. They're not doing anything anymore. They're supposed to continue up, but they're not. And they're starting to pull the control rods out further, and nothing's happening. It's like pushing on your gas pedal in your car, and you're not going any faster. And as they're working with this, even with the control rods all the way up, power continued to drop. By 6:30 p.m., about 18 hours after startup, the reactor is dead. They got about $100 million invested in this thing, and it is dead. Now what do you do? And then it began to recover. By 1 a.m. the next day, it started operating at low power. Eventually, it goes back up to 100 megawatts, and then it begins to shut down. It's pogoing. A full power, dead, full power, dead. Only it's not full power, it's like half power, and then dead. The behavior, start up, climb to 100 megawatts, shut down, rest for about 11 hours, and then climb back up to 100 megawatts, only to shut down again. Convinced Wheeler the reactor was poisoning itself. The poison had to be a fission product that was gobbling up so many neutrons that there weren't any for the fission and capture of the U-235 and U-238. The fission products ate up the neutrons, then its half-life caused it to decay. So for 11 hours, when this thing is doing nothing, what he's thinking is that there's something out there with a half-life of roughly 11 hours, and then it's decaying into something else, and it allows the reactor to take off again. Can you see that?
Yeah.
Okay. Wheeler figured the poison must have a short half-life, decaying after about 11 hours to a point where the reaction could start up again. Wheeler determined it had to be Xeon-135 with a half-life of 9.2 hours. Xeon-135 turned out to be a daughter of another fission product, iodine-135. It would turn out that Xeon-135 had a cross-section 150 times higher than the most absorbent material then known. So, what do? You got $100 million invested in this thing and it doesn't work. This doesn't look good on a resume. This is reactor B. Now, there are two other reactors that they're building. All right, this is reactor B, and then there's a reactor D, and there's a reactor F. But this is reactor B. This is in Hanford, Washington. And this is another shot. This is reactor B. Can you see it right here? And these towers, these water towers, these were put here in case they lost cooling water. They would use the water from here to keep the thing cool so they could get the thing shut down. They never had to. This is reactor B. There's the reactor. And you can see there's a tour going on. This thing's been shut down for 30 years, but this is a reactor. And it's a graphite box, 36 feet high, 36 feet wide, 38 feet deep. There are 1,504 aluminum tubes drilled horizontally, completely through the graphite. And these 1,504 tubes are drilled in kind of a circle like this. There are 200 tons of uranium slugs filling the 1,504 aluminum tile tubes in the 1,200-ton block of graphite. What Wheeler decided to do is, again, these tubes, you can see them here, all these little pieces that are sticking out, that is the end of one of those tubes I'm talking about. He said, we're not going to drill, they already drilled them. You're going to connect 500 more tubes, and now we're going to have 2,004 tubes, and we're just going to overwhelm this fission product that's sucking up all the neutrons. We're going to have so much fission going on that it's still going to work. Now, what happens is, here's an elevator right here, and it goes up and down, and men stand on this elevator, and these tubes, again, they're horizontal, and you crack open a tube here, and you start loading this, and you load it with uranium slugs, and the uranium slugs are about the size of a roll of quarters, and they're clad in aluminum, and it took months to figure out a way to clad these things in aluminum so that you didn't have hot spots. The uranium has got to be in constant touching of the aluminum, and you had to seal these things so they don't break open, because you got river water going through here, and if these things break open, the radioactive products are going to get in the river water and end up in the Columbia River. This is not a good PR move. It takes months to figure out how to make these aluminum slugs so they don't leak. They had to make 70,000 of them, and each one was fluoroscoped, visually inspected. They had all kinds of tests to make sure these things were right. 70,000 of these things. So now on this end, you pop the tube open and you start shoving these uranium slugs in here, 38 feet of them. Now, the reactor isn't right here. There's 6 feet of concrete between what you see here and the first graphite. Otherwise, this room would be so radioactive you couldn't go in here. But it's 6 feet of concrete, and it's covered in cast iron and all kinds of other stuff. Otherwise, these people would have been dead a long time ago. So can you see this? You have these guys popping these things open and shoving these uranium slugs in here, 38 feet of them. And then they have to close all these tubes up, and you start up the reactor. And the tube is about this big around. Columbia River water is going through the tube, pulling the heat away from these uranium slugs, and then going back to the Columbia River. Can you see that? All right. It cooks for about 100 days. And then they there's a room. Every one of these 2004 tubes has got a temperature gauge attached to it. 2004 temperature gauges. Because they want to know how hot each tube is, because if a tube is running hot, it is cooking, and the uranium is further along the process of the beta decays that they want to have happen, and they want to pull the slugs out of that tube first. Okay, because that cake is done. Right? So, cooks for 100 days, they shut the reactor down, and now these guys get up on the elevator and they pop open the tube, and there's another guy on the other end of the reactor, like this. He pops open the tube. They take high pressure water and they start pushing these uranium slugs through there, and they fall into a big pool of water, and it would be in the page back there about 40 feet or 50 feet. And they fall into this big pool of water, and they do that with all the tubes that have cooked, and the cake is done. Right? They let the uranium slugs sit in this pool of water for 2 or 3 days to let some of the really, really nasty fission products decay away. Is this cool or what? When they added the 500 tubes, it overwhelmed the fission products that were sucking up the neutrons, and now it's cooking. And Reactor D that I was talking about, it went critical with 2004 tube loading on December 17th. Reactor B, it had started up in September. It was dead for 3 months while they were hooking up all these 500 tubes. And now it's running at 250 million watts, and it starts up on December 28th, 1944. We are 7 months to Trinity, and you're just getting the reactors to work. Fuel near the center of the reactor was subject to a higher number of neutrons and required less time. And this is where they used the high pressure water to push the slugs out, and then they would fill it up again with new slugs for the next batch. Usually about 25% of the channels would be discharged during each shutdown, accounting to 60 or so tons of irradiated fuel. 60 tons of this stuff. Okay, for every 2 tons of uranium you start with, and you cook it, you hit it with neutrons, and this chemical process is taking place, and you're splitting the U-235, you're making fission products, and you're making plutonium. So you start off with 2 tons of uranium, now you have the fission products, and you have plutonium, and the plutonium is mixed in here. The amount of plutonium you're going to have has a volume of about a US dime. You start with 2 tons, and you're going to have plutonium of about the size of a dime. And you've got to pull that out of this 2 tons of stuff that you've irradiated. This is the T plant. It's called the Queen Mary, and this is where you're going to extract the plutonium from all these uranium slugs. The 60 tons of stuff that you pulled out of the reactor is going to go here to be separated into plutonium. The T plant, they were called Queen Marys because they were longer than a Queen Mary. And it's mostly concrete, 875 feet long, 90 feet wide, and about 100 feet high, although about 20 feet was below ground. Long, narrow canyon with a roof, operations in the galley above the cells using remote control tools to perform the tedious step-by-step chemical extraction of plutonium developed by Grant Seaborg's group in 1943. A stupendous billion-time scale-up from laboratory procedures and test tubes. Operators pump the mix from cell to cell, the plutonium concentration increasing with each step. Each ton of irradiated uranium that went in one end of the Queen Mary contained about 8 ounces of plutonium. Seaborg wrote later that for a while, at least, tons and tons of material were shipped into Hanford, but nothing ever seemed to come out. This is the inside of one of the Queen Marys, the T plant where they're separating this stuff. Again, there are 40 cells, and this is what it looks like on the inside. A standard equipment occupied 2 cells: a centrifuge, a catch tank, and a precipitator, and a solution tank, all made of specially fabricated corrosion-resistant stainless steel. The liquid solution that the slugs had become would move through these units by steam jet siphoning, a low-maintenance substitute for pumps. There were 3 necessary steps to the separation process: solution, precipitation, and centrifugal removal of the precipitate. These would repeat from equipment group to equipment group down the canyon. The end products would be radioactive wastes stored on site underground tanks in small quantities of highly purified plutonium nitrate. Plutonium nitrate is a brown syrupy liquid, and this is what's going to get shipped to Los Alamos. At Los Alamos, they will pull the plutonium out of this syrupy stuff. Reactor B slugs traveled by rail to the T plant beginning on December 28th. I think this is a mistake. I don't think it was then. I think it was later. The yields in the first plant runs ranged from 60 to 70% and reached 90% early in February 1945. So they're getting most of that dime's worth out. They're getting 90% of a dime's worth out. of the process. This is the inside again. This is where the operators were. And you can see there's a lot of concrete here. And this is where they're decommissioning the Queen Mary. They're cleaning it up because it's been decommissioned. But this is what it looks like. And then the plutonium is shipped to Los Alamos. Groves was enthusiastic enough at the end of 1944 to report to George Marshall that he expected to have 18 5-kilogram plutonium bombs on hand in the second half of 1945. So this is our plutonium. Things are working. Now, I told you about gaseous diffusion. The membrane, and I still cannot believe this, the membrane, and there are miles of this stuff turned into these tubes. Every square inch of this membrane has hundreds of millions of little holes for the U-235 to go through. Now, how do you make something, a square inch, that's got several hundred million holes in it? And this had to be plated with nickel because this uranium hexafluoride is going to eat through just about anything you can find. All right, so all this stuff has got to happen. They've got to have square miles of the sheet for the porous barrier. And they get it done. They build a plant, they're going to manufacture this stuff, and then somebody comes up with a new material, and they said, okay, we need to tear all this thing out of the plant because this new material is better. And all these decisions have to be made about whether or not this is going to work. And this is the K-25 plant at Oak Ridge. This is 43 acres under one roof. And this is where gaseous diffusion is going to take place. And you can see vehicles out here. Those give you an idea of the scale of the building. This is a map of Oak Ridge. And again, there's 59,000 acres here. This is the city of Oak Ridge that they created. And this is where Y12 is going to be. Y12 is electromagnetic separation. And this is K25. This is gaseous diffusion. And this shows where this is in Tennessee. Here's another shot of the K25 building with the gaseous diffusion. There are thousands of cascades in here. And when they get all this stuff to work, there could not be a speck of grease in the miles and miles of pipes. If it did, the uranium hexafluoride would attack it and it would just make it. They would have to go in and clean the pipes out because it would just make a mess. You can't use grease for the bearings. So what do you use? They used Teflon. How did they know about Teflon? This is early 1940s. There was no Google.
DuPont had the contract.
No, this was actually another company at it, but they figured it out. They figured it out.
Did Teflon exist before this?
I have no idea. But anyway, they used Teflon for the bearings and the seals. A single pinhole leak anywhere in the miles of pipes would confound the entire system. It took 200,000 cubic yards of concrete and was started in October 21st of 1943. Enrichment for gaseous diffusion in the most advanced automated industrial plant in the world had begun. It would proceed efficiently with only normal maintenance for decades. Early in 1945, Oak Ridge began shipping bomb-grade U-235 to Los Alamos. The yields in the first plant runs ranged from 60% to 70% and reached 90% in February of 1945. This is the control room for K-25. Look at all the stuff that they had to build, ship to Oak Ridge, and put together and hook up and make this stuff work. And this is a look down from K-25. You can see a guy back there on a bicycle because you'd be exhausted running yourself through all this. And I still find it incredible when you see all of the stuff in here. All of it had to be built and shipped and hooked up and running in a matter of months to get all this stuff done. All right, this is Y12. This is an aerial view of Y12. This is where the electromagnetic separation took place. And you can see all the stuff that had to be built to make this stuff happen. And, oh, come on. This is a schematic of the process. And you have two ion beams, one for U-235 and one for U-238. And the difference between these two beams right here is 3/10 of an inch, about that much. So you got U-235 coming in here and U-238 coming in here, and there's 3/10 of an inch difference. And if the operators don't get it right, they end up with U-238 with the U-235, and they get U-235 in with the U-238. Okay, so the operators are crucial to making this thing work. And the operators have no idea what they're doing or why they're doing it. All they know is they need to do it, because everything is a secret. We talked about calutrons. Here's Y12. We got to build magnets, thousands and thousands of magnets. And Grove says, okay, what metal do we need for the magnets? And then they said, well, how about copper? And somebody says, there's a war on, there is no copper. How about nickel? There's a war on, there is no nickel. And they keep working their way up through the metals until finally they get to silver. And they go to the Treasury Department and said, we need silver. And the Treasury Department says, how much do you need? And they said, we need 395 million troy ounces of silver. 13,500 tons of silver. A typical flatbed tractor trailer today, its payload is about 40,000 pounds. It would take over 600 18-wheelers to move that much silver somewhere. Okay? So the silver shows up, it gets melted down from these little itty bitty pieces into bars. The bars are shipped off to Milwaukee. Aldous Chalmers gets them. They got to turn this into wires. They've got to turn these into windings for the magnets. They have to put these into these steel cases. They have to put the oil in there for cooling and weld it shut and then ship all this stuff to Oak Ridge. I can't imagine this getting done in any reasonable length of time, but it is. The bus bars, these racetracks, you need enormous amounts of power for these magnets. So the bus bars that carrying the power around are 1 square foot of solid silver. Okay? They're building these buildings and they're putting in these calutrons to do this electromagnetic separation. He's building some and then he's building more. They can have up to 90% U-235. Alpha and beta buildings would eventually cover more area in the valley between these two ridges than 20 football fields. They call them racetracks because they were shaped kind of in an oval like a racetrack would be. And they were mounted on the second floors, and the first floors had monumental pumps to make the vacuum. Eventually, the Y12 complex counted permanent buildings, large and small. The Calutron buildings of steel and brick, tile, chemistry laboratories, distilled water plant, sewage treatment plants, pump houses, and all this other stuff. All this stuff had to get built. And this is what it looks like. This is a racetrack. This is the first design that they came up with. And this is the Calutron. This is where they're separating the U-235 from the U-238. And here's a magnet, Calutron, magnet, Calutron, magnet. You can see here, Calutron, magnet, Calutron. This is where all the windings are for these. And here's the bus bar carrying the power to the magnets. 1 square foot of solid silver all the way around. This is 122 feet by 77 feet by 15 feet. to get all this stuff done. For an output measured in the best of times, grams per day. Faced with new estimates from Los Alamos that an efficient uranium gun would probably require 40 kilograms, Groves brought Lawrence's proposal to a doubling, adding 4 new 96-tank tracks of advanced design designated Alpha 2 and a proportionate number of beta tracks at a cost of $150 million, more than $100 million already authorized. If everything worked at Y-12, Groves justified his proposal to the Military Policy Committee. They would then have a 40 kilogram bomb core around the beginning of 1945. The Army had contracted with Tennessee Eastman, a manufacturing subsidiary of Eastern Kodak, to operate the electromagnetic separation plant. By late October of 1943, when Stone & Webster finished installing the first Alpha racetrack, the company had assembled a workforce of 4,800 men and women. They were trained to run and maintain the Calutrons without knowing why, 24 hours a day, 7 days a week. Inexperienced operators had trouble striking and maintaining a steady height, a steady ion beam. Groves recalled that the powerful magnets unexpectedly moved the intervening tanks, which weighed some 14 tons, out of position by as much as 3 inches. The problem was solved by securely welding the tanks into place using heavy steel tie straps. This is what it looks like. And you can see the magnets here as we go around. You can see the reinforcing for the magnets because these things are just chewing up an enormous amount of power, and then in between them are the Calutrons for the separation of the U-235. These are Calutrons. These are extra ones. They're sitting here waiting to do something. And these are, what are these? These are the Alpha 2. These are the new design for this. The racetrack design proved to be really too hard to deal with, to work with. And so they came up with a new design. But again, you still have the magnets. You can see the bus bars. They're covered up with something to provide the power. I read, and when you think about all these magnets, when you think about the pumps at Hanford and the gaseous diffusion, all of the pumps pumping this stuff through here, I read that 10% of the power, of the electrical power in the United States, was going into Oak Ridge and Hanford to run this stuff. Wow. So these are the Alpha 2s, and these are I think these are the betas. Yeah, these are the beta ones. And again, you can see these are smaller. These are doing the finishing. You're getting up to like 60% U-235, and now these are taking you up to like 90% concentration of U-235. And these are the bus bars over here on the sides. The magnets started shorting out. They thought that there was moisture and the moisture would evaporate, but it didn't. It got worse and worse and worse. They had to open up the magnet covers. They found that these they had miscalculated on the magnets. The wires were too close together. They were shorting, and the oil they were using had too much rust and stuff in it, contributing to the shorting out of the magnets. They had to be shipped back to Milwaukee. They had to be cleaned and rebuilt, and then shipped back to Oak Ridge to make this process happen. The Calutrons produced 100 grams per day of 10% U-235 in late September 1944. If you want bomb-grade uranium, it's about 90%. 85% of some 864 Calutron tanks operated to produce 258 grams, 9 ounces of 10% enriched product. And sufficient enrichment for a bomb, January 6, 1945, Conant calculated that a kilogram of U-235 per day would mean 1 gun bomb every 6 weeks. And this is January of 1945. your 6 months of Trinity. These are the operators running the calutrons, and that is Gladys Owens. But they are actually controlling the ion beams that are taking place here, and they've got to sit here and watch this thing. They got to be very good at this. They would make phone calls like, you're losing heat, you need to increase the heat for this, or you need to do this. They really got to be good at this, and they still did not know exactly what they were doing. But by the time they had been in here for several months, they started to figure it out. These were not stupid people. These are the operators for this is a different set of operators. You can see this is a different setup. And you see, they're seeing, I wish I could see what that screen is. I wish I knew, because you can see, like this lady is turning a dial to dial in this to make it more effective. You can see how much concentration there is in all these people trying to make this stuff work better or work right. And this is the reason that the racetracks, they stopped using them. This is how you empty the buckets of U-235. You had to take them out of service, you had to put them on this fixture, and you had to tip them up. It's like a vending machine. We're going to take the money out of the coin slot, we're going to turn it over to empty the coin slot. That's essentially what you're doing here. Okay? All right.
Were they getting more 235 out of the gaseous diffusion or more out of the calutrons?
It was mostly the calutrons. The gaseous diffusion plant really didn't come online until January of 1945.
Okay.
Okay? That's a good question. There's so many dates and stuff mixed into this that after a while it all just becomes kind of a fog. So now at this stage of the game is January of 1945. We're producing U-235 at the right rate. We're producing plutonium. It's being shipped to Los Alamos. And now we get into the bombs. Now, you realize there are two different bombs. One is uranium-based, the other is plutonium-based. And the uranium-235 bomb is called Little Boy. And the uranium bomb, take an artillery barrel. You have guns, fire shells. You take a barrel, you cut it so it's about 6 feet long. You put a hemisphere of U-235 here. You put a hemisphere of U-235 here. Now it's not a hemisphere. It's different shapes than that, but you get the idea. You explode here. This one comes down at 3,000 feet per second and hits this one. Boom. Nuclear explosion. That's it. That's all there is. So this was pretty straightforward. And in the autumn of 1943, Segre, he's one sharp dude. He's working with spontaneous fission of uranium and plutonium. He finds that with proper shielding, the uranium bomb doesn't have to be 17 feet long. This was a thin man bomb and could be just 6 feet long. So it was renamed the Little Boy. But this is pretty straightforward. I mean, it's a nightmare to get all this stuff packaged, but we're ready to go with the uranium-based bomb. Compared to the design of the U-235 bomb, the plutonium bomb, Fatman, was a nightmare. Los Alamos, they bought the boys' school in December of 1942. The Army Corps of Engineers shows up and they start building the buildings and the labs and all the facilities for Los Alamos, and the scientists started showing up in March of 1943. So you're 2 years and 4 months from Trinity. And in April of 1943, they have a meeting and they're trying to figure out how the bombs are going to be built. And they realize that plutonium is going to be a problem, or they think it's going to be a problem. And Seth Niedermeyer comes up with the idea of implosion. We'll put a whole bunch of explosives around a plutonium sphere and we'll explode them, and the plutonium sphere will become a smaller sphere, it will go critical and it will go boom. How hard can it be? And he became a gigantic pain because he said, we need to do the implosion. Hans Bethe, he was the head of theoretical division. He said, plutonium, the implosion, it's not going to work. Oppenheimer doesn't think it's going to work. But Neddemeyer keeps after them, and finally, Oppenheimer says, okay, if it's that important to you, you're in charge of making implosion work. Again, be careful what you wish for. And Neddemeyer spent all of 1943 trying to get implosion to work. He's just taking pipes, metal pipes, and wrapping them with explosive. And they're putting detonators in different places. They're using different thicknesses of explosive, and they're exploding these. And they want this to get smaller. They want it to be this diameter, and then they want it to be a smaller diameter. And all they're getting is a very mangled pipe. It is not anywhere near a sphere or have a radius. It's a mess. Remember plutonium-240? We talked about back there? There's plutonium-240 in with the plutonium-239, and it creates spontaneous fission. And they found that if you try to do the artillery shell, the artillery barrel, that if you have plutonium here, and you fire this at 3,000 feet per second, before these will ever get together, it will start melting down. Hence plutonium-240. And what you're going to end up with is a pop instead of boom. So you can't use the artillery barrel with plutonium. And all of a sudden they realize it's got to be implosion to make this work. And when they started out at Los Alamos, they thought they could do this with 235 physicists. And in 1944, they're way over 1,000, and they keep hiring every physicist they can find because they cannot solve the implosion problem. It is a nightmare. Neddemeyer can't get it to work at all. Oppenheimer decided they would throw the book at implosion. In the months ahead, the laboratory, which had swollen to 1,200 full-time employees by the previous May 1st, would once again double and redouble in size. Going crazy trying to get implosion to work. Neddemeyer cannot get this to work. Hans Bethe summarized absolutely awful results. Now, you're exploding something to see if something is going to go from this size sphere to a smaller sphere. How do you know how well it's going? So they developed X-ray equipment that had to obviously be far enough away so that the explosion did not destroy the equipment, that would pulse as rapidly as 10 millionths of a second. And they could put this on film so they could see how the implosion was going. They had a lot of sharp dudes there, and 10 millionths of a second to get these pulses going, these X-ray shots, took some really sharp dudes, but they did it. Now, getting all these shock waves to work was the problem. And I want to show this because this is the heart and soul of this whole thing. If you have, here's our sphere of plutonium, and you detonate something here, and it's going to have a shock wave, and the shock wave is going to go like this. These are convex. They're going to come in, and they're going to hit this, and then you have another one over here, and it explodes at the same time. It's going to come over, and it's going to hit this. Well, this is going to get pushed in, and this is going to get pushed in. And if you have one up here coming in like this is going to get pushed in. And if you have one here, you're going to have the same thing. This is going to get pushed in, this is going to get pushed in like this. And this is going to get pushed in like this, and like this, and like this. The problem is this, and this, and this, and this are going to shoot out like toothpaste out of a toothpaste tube. And that's what they were running into. These convex shock waves are not going to work. with a sphere. It is not going to happen. Who solves the problem is John von Neumann. He's the mathematician from Hungary, and he's the one who figures it out. And I'll show this in a second. I gotta present something first. This is the Fatman bomb. And around here, these are the explosives. At the end, there are 96 of these explosive blocks around here. And this is the uranium tamper. You see that? And this is a little trap door that you pull open so you can put the plutonium core inside of here. That goes inside here. This is uranium. This is a big sphere of uranium. And the reason for the uranium is when the plutonium is when it is starting to fission, some of the neutrons are going to get away. And the neutrons are going to fly off and they're going to hit the uranium, and the uranium being very, very dense, they're going to bounce back into plutonium and continue the fissions. So that's the only reason the uranium is there, to direct the neutrons back into the plutonium. There are 96 of these blocks of explosive. They got to be called lenses because you were focusing the shock wave much the way that your glasses focus light. These are focusing the shock waves. And they were designed, again, to focus the shock wave so that you would turn this into a smaller sphere than what you have. And this is a face of one of those blocks of explosive, to give you an idea of what von Neumann came up with. This is in mid-1944. Here's your detonator, and there's your explosive. This is high explosive. It burns very, very fast. And this piece right here is low explosive. It burns more slowly. This fires, boom, and here comes a shock wave. And when the shock wave gets to the low explosive, it starts to deflect the shock wave so that it becomes a straight line, and then it bends around this, and it changes shape to now it's no longer convex, now it's concave. And when it gets to here, when it gets to the uranium tamper in the sphere, this shock wave is the same diameter as the uranium sphere. And you've got these all the way around, and all these match up with the uranium tamper and ultimately the plutonium to push this whole thing in, so it'll be symmetric. Now, you really don't have any computing then. And von Neumann comes up with this idea, everybody loves it, it's perfect. The problem is now we got to get it to work. And there's a guy named Kostakowski, he's in charge of the explosives, and it's his job to figure out how to put this into something that will work. They start exploding roughly a ton of explosives every day, trying to figure out what they have to have for these lenses to make this work. They are pulling their hair out to get this thing to work. The high explosive had to be learned by trial and error. In February of 1945, Kostakowski chose an explosive called Composition B to serve as the fast-burning component of Fatman's lenses and mixture he had commissioned from the Navy Research Laboratory. Baritol for the slow-burning component. Composition B was poured as a hot slurry of wax, molten TNT, and a non-melting crystalline powder RDX that was 40% more powerful than TNT alone. barytol slurried barium nitrate and aluminum powder with TNT, whatever that word is, and nitrocellulose. We learned gradually that these large castings, 50 pounds and more each, had to be cooled in just certain ways. Otherwise, you got air bubbles in the middle of separation of solids and liquids, all of which screwed up the implosion completely. So it was a slow process. The explosives were poured in, and the people sat over that damn thing watching as if it were an egg being hatched, changing the temperature of the water running through the various cooling tubes built into the mold. Each one of these 96 pieces has got a separate mold. You can see that they're all different shapes. And so these molds, these molds for these explosives, they got to make all of these, and again, the cooling stuff has got to be in there, and they've got to make all this happen. You've got hundreds of people in the machine shops making these things. We were consuming daily something like a ton of high-performance explosives made into dozens of experimental charges. The total number of castings, counting only those of quality sufficient to use, would come to more than 20,000. X Division managed more than 50,000 major machining operations on those castings in 1944, 1945, without one explosive accident. A test on February 7, 1945 showed definite improvement in implosive symmetry. On March 5, 1945, after a strained round of conferences, Oppenheimer froze lens design. He thought they had it. However scarce plutonium might be, no one doubted that Fatman would have to be tested at full scale before a military weapon could be trusted to work. The initiator. You have an explosion, the shock waves come down, and they make the plutonium from being a small orange down to the size of a walnut. A sphere that's the size of a small orange down to the size of a walnut. And the problem is, if there is no neutron to start the fission process, like we had over there, all you have is a very expensive explosion. There is no nuclear bomb. You've got to have that neutron to get things started. So they have to create an initiator, something that's going to give off neutrons when this plutonium is crushed down to a different size sphere. This became probably one of the most classified things in the nuclear arsenal. But they think that what they were using was polonium plated with beryllium, and the beryllium had dimples in it to create turbulence, so there would be mixing. Polonium gives off about 90 million neutrons a second. So in the 10 millionths of a second that this process is happening, you should have 9 neutrons that will be available to start the fission process, to begin the nuclear explosion that you need from plutonium. They use this same initiator in the Little Boy bomb. So when the two pieces of uranium come together, they know that they're going to have neutrons to begin the process.
Polonium's stable. You can have the initiator sitting around on the shelf while you wait to deploy the bomb.
How stable it is, I do not know. They made them, polonium, for what it's worth, it was discovered by Marie Curie, and it was named after Poland, where she was born. That's one of the issues in the nuclear arsenal. What is the shelf life of this stuff? Again, you do not want to have an explosion where there's no nuclear piece. That doesn't do you any good. For the initiator to find something that would work, and the initiator was about the size of a hazelnut. You can think of the plutonium as a peach, and the plutonium itself is the peach. The nut, the seed inside the peach, that's where the initiator went. That's what the initiator was. And it's about the size of a hazelnut. Okay. The initiator group, when they were designing the initiator, they drew blind holes in large turbine ball bearings. They called them screw balls. Inserted test initiators and plugged the holes with bolts. After imploding the screw balls, They recovered the mains and examined to see how well the plutonium and beryllium had mixed. Beta's committee selected the most promising design on May 1st, 1945, but only a full-scale test culminating in a chain reaction would prove definitely that the design worked. May 31st, 1945, enough plutonium arrived at Los Alamos from Hanford to begin critical mass experiments. Critical mass is how much do you need so that a neutron, starting from the center of this thing, will fission something before it escapes. That's what a critical mass is. Fisher's group confirmed the core configuration experimentally on June 24th, 1945. For the high-density form of plutonium, the critical mass is 11 pounds. Even with a nut-sized central hollow to hold the initiator, the Trinity core cannot have been larger than a small orange. As of June 9th, 1945, Kistikowski did not have enough quality lens castings on hand to assemble a complete charge. Oppenheimer further compounded his troubles by insisting that on firing a copy of the bomb a few days before the Trinity shot to test its high explosive design at full scale with a non-fissionable core. Each unit would require 96 blocks of explosive. It's Sunday. Trinity's happening in a few days. He does not have enough of these explosive pieces. And he talked about the problems of having air pockets inside some of these. And he was afraid these air pockets were going to screw up the implosion. So he's in a jam. He's got to get this done. And so finally he runs everyone out of the building, and he's taking these blocks of explosive that have the air pockets, and he's sitting them on his lap, and he takes a dentist drill. You can't have sparks. And he's drilling down into this to where the air pocket is, and then he's pouring high explosive into this to fill up the air pocket and then fill up where he's drilled into this. And that's how he's finishing the last pieces of lens for this thing. And he said, at first I was concerned, but then I realized if anything went wrong, I wouldn't know it anyway. And so he just went on and did it. To give you an idea about Kistikowski, he's a cool dude. He gets to play with explosives. He liked to ski. And they had this hill at Los Alamos that was perfect for skiing, but it had trees on it. So what he did is he took pieces of explosive and he made necklaces around the trees, exploded them, and then he got the Army Corps of Engineers to push the logs off his hill so he could go skiing. Is that cool or what? All right? All right. This is the X-ray shots of the implosion. And you can see at the end it getting smaller, and that it's symmetric. This is what I'm talking about, the 10 millionth second X-ray shots of the implosion process. Okay? So they have Trinity. Trinity is south of Albuquerque. If you go down I-25, you get to San Antonio, you turn left, and you can drive into the Trinity test shot place. It's open twice a year, the first Saturday in April, first Saturday in October. It's a cool place to go. Again, this is where the first atomic bomb was exploded.
So was that a plutonium bomb?
Yes.
Or you built a plutonium bomb?
Yeah, because it was so complex.
Okay.
Oh, I forgot. This is a museum in Los Alamos. I took these pictures. This is a little model of the bomb. Now you've got 96 pieces of explosive, and you're going to put detonators on 32 of these to explode. You've got to have something that's going to send the sparks out to 32 places, and they all have to explode at identically the same time. Now today, you would probably create a circuit to do this. In 1944 and 1945, how are you going to do it? How are you going to make this happen? This is the fire set. This is the thing that's going to send the sparks out to explode the bomb. And these are the wires that are going to send the sparks out. All the wires obviously have to be the same length, because again, all these sparks have got to reach the detonators at the same time. These wires, these are spark plug wires off of aircraft engines that they're using here. And this is what this looks like. And there's the bomb on the Trinity. This is the top of the tower at Trinity. And you see that the fire set goes right in here. And you see all the wires going out to these. One of the problems they had is the detonators, they didn't think they were going to work. So at every place on those 32 pieces where they have the detonators, they have 2 detonators there, hoping that one of them will work. Just another nightmare. Okay, they want the bombs to explode at 1,900 feet. And how do you get something to explode at 1,900 feet? And what they decided to do, this is the Fatman bomb at the museum in Los Alamos. And what they did is P-51 Mustangs had a radar in the tail. It was called an Archie. And the idea was this radar would tell the pilot if there was somebody behind him. So they took these Archies, these radars from the P-51 Mustang, and they put them in the bomb. And there's an antenna, there's a radar antenna, there's a radar antenna. There are 4 of these all together on the bomb. And each one of them is obviously sending out a radar signal. And the first one to 1,900 feet wins, and that explodes the bomb. So that's how that takes place. One of the things they were worried about is sparks. You're going to put this thing in a plane, it's going to be flying around, and if you have static discharges build up, if a spark gets into one of those spark plug wires and explodes a piece of high explosive, it's not going to be a nuclear explosion, but it's going to blow the plane up. And a lot of very expensive plutonium is going to be scattered all over the ocean. So they were concerned about these stray sparks, and what are we going to do about these? And at sea level, the place they're going to take off from is Tinian. It's at sea level. At sea level, the air is so dense that the chance of a stray spark getting through that air is not going to happen. The number is so small, it's not going to happen. The problem is at 30,000 feet, when the air is a lot thinner, the spark could get through there. So somebody said, what if we make the bomb think it's at 30,000 feet? So what they did is they went to auto supply houses and they bought gasket material and automotive stuff, and I used to know the brand name, but I've forgotten it. And what they did is seal the seams at Trinity, or at Tinian, so that when they loaded the bomb into the plane, it would always think it was at sea level. So this paint you see here, this brown paint, this is to seal the seams so that no air can get in or out, so the air pressure inside the bomb is going to be at sea level. Okay? This is the Little Man bomb. You can see it's got the radars on it. Again, there are 4 of them. This is a front view of the Fatman bomb, and you can see the 4 radar antennas. There's 1, 2, 3, and 4. And again, there's the brown stuff, the gasket material, and this special paint coating to seal the bomb. This is Tinian in the South Pacific, and here's Japan, here's Iwo Jima. This is the route the plane took to drop the bomb on Hiroshima. Tinian is about the size of Manhattan, and they built 6 runways there, each one 2 miles long. And there were hundreds of B-29s there. And every afternoon, a plane would take off every 15 seconds for an hour and a half off these 6 runways. heading to Japan. Japan still had planes, but they had no pilots. And these B-29s could fly at 30,000 feet because they had oxygen. The planes the Japanese had couldn't go above 12,000 feet. So what this means is that these bombers were unopposed. They could fly anywhere they wanted to over Japan and drop bombs on anything they wanted to, and they were not going to be stopped. The biggest problem they had was the jet stream pushing the bombs off target. And they were just blowing the tar out of Japan. In March of 1945, they firebombed Tokyo, and in one night, they burnt 15 square miles of Tokyo, and they killed over 100,000 people. But they were just laying waste to Japan. So the bombs are going to take off from Tinian, and these are the routes they took to get to Japan to drop. This is a museum in Albuquerque where I took this picture. Here's the B-29, and here's the Little Boy bomb. The bombs are so big that they had to dig a pit that they could push the bombs into and then load them up from there into the planes. And you can see the pit here. And you can see a name right here. It's too small kind of to read. This is Paul Tibbets. He's the pilot of the first bomb, the first plane to drop an atomic bomb. He was in charge of the whole shooting match. These B-29s, they were called silver plate. They were specially designed to carry nuclear weapons. And he was the one who was in charge of training the crews to carry these bombs. And he flew the first mission to drop the atomic bomb on Hiroshima. He found a sign painter, and he had him put Enola Gay on the plane. And when he was growing up, he wanted to be a pilot. And his dad said, "You're an idiot. You're just going to get." Think about flying in 1930s. It is dangerous. And his dad said, "You're an idiot. You're just going to kill yourself. This is stupid. I don't know why you're doing this." They would have these enormous fights. And when they were over, his mom would always say, "Go ahead. It'll be all right." She always did that. She always encouraged him. That's his mom's name. His mom's name was Enola Gay Tibbets. And Enola is alone spelled backwards. That was his way of saying, "Thanks, Mom." Okay? So, Enola Gay drops the bomb on Hiroshima. 3 days later, on August 9th, they dropped the Fatman bomb on Nagasaki. The name on that plane was Boxcar. I don't remember the pilot's name. And that's kind of the end of the story. I want to show it. This is the Trinity test site. I took this picture. This is the parking lot. I'll give you an idea of how many people are there. This is in October of about 7 years ago. And this is walking to where the bomb was exploded. And the tower was 100 feet high. It was vaporized. This is July 16, 1945. The tower was vaporized. And this little obelisk, they put that there right where the tower was to show where Trinity. And this is a placard that shows the way to head to White Sands Missile Test Range to the Trinity test site. And it says, J. Robert Oppenheimer, director of the Los Alamos Nuclear Physics Laboratory, who said at the blast, "Now I am become death, the destroyer of worlds," quoting from the Bhagavad Gita. So, I want to find this. There it is. Listen.
Нет, так это же не на таком, в общем, посреднем, на низком уровне. В основном это была группа ученых, которая составляла основная группа ученых, была 12 лет.
Did you hear the language that those people were using? Could you hear it? I'm walking into the museum at Los Alamos, and there's this big bus that's just pulled up. And these people are getting off, and they're speaking in a language that I have no idea what they're saying. And I walk up to this lady who is the tour guide for this. And I said, where are the folks from? And she said, they're from Russia. They came here to find out the truth about the bombs. They had come all the way from Russia to come to Los Alamos to find out about the bombs. And I thought that was kind of cool. I'm kind of tapped out. If there are any questions, I will try to answer them. I went pretty fast. I'm sorry about.
Got two, real quick. Where did all the uranium come from? Was it being used for something else? I mean, it had to be mined. So there had to be a scale up of the uranium mining process.
He doesn't really say, Rhodes in his books, he doesn't really say where the uranium comes from.
I mean, I know it's mined, but
Yes.
that had to scale too, right?
Right.
Because we go from a laboratory sample to tons and tons and
Yes.
tons and tons.
I honestly don't know. At the end of World War II, the Germans surrendered in May 10th, and Groves had sent people to follow the army through Europe looking for uranium to see what the Germans had done with this in their own atomic bomb project. And they found barrels of uranium in places, and obviously that was shipped to the United States. There was a company that had boatloads of this stuff stored in a warehouse somewhere near Manhattan, maybe Long Island, I don't remember exactly where, that had come from the Belgian Congo, and we bought that immediately to use for the project. But after that, I don't know.
And there was a play that I happened to attend at the Purple Rose Theater about when the first test went off. And one of the physicists was at a bar, and it was a very good play, but in the play's language where I get most of my information, I don't dig deep like this, I just surfaces. The physicist said there's a 20% chance or 30% chance we'll ignite the atmosphere.
Okay.
Is that true?
Okay.
Was there that thought that they might do that?
He's my straight man. He's my straight man. And when they first got these guys at Los Alamos, there's a lot of really smart people. And somebody showed that if you explode a nuclear weapon in the atmosphere, it will light the nitrogen on fire. And the air is 70-some% nitrogen. So if you start burning it, we're going to have a bad day. All right, that means the end of the world. And later, some of the other physicists who were a little sharper said that this is nonsense. It's not going to happen. So early in July of 1945, a whole bunch of these guys are heading down to Trinity to watch the test. And one of them is Edward Teller, and he's walking with a guy named Robert Serber. Teller's from the city. He doesn't understand country, all this stuff. And he said, if we get down there and I step on a rattlesnake and it bites me, what do I do? And Serber says, I'll bring a bottle of whiskey. That'll take care of it. And Teller thinks, oh, that must be the cure, so we're fine. And they're walking further, and Teller says, you know, when we first got here, we were thinking that when we explode the nuclear weapon in the atmosphere, it's going to start the nitrogen on fire. And he says, do you think that's going to happen? And Serber says, we'll take 2 bottles of whiskey. I had another story, but I don't remember. I lost it.
So the Germans really were working on an atom bomb because they had uranium, but they never came close to anything like this. If you did all this stuff,
Right. The Germans had some incredible physicists, They had a boatload of them. I mean, these guys were amazing. And every time you see it brought up, they were ahead of us in the physics of this, way ahead of us. Things that we stumbled over, things that we had to do experiments on, they had figured out theoretically. So they were way ahead of us. One of the problems was a moderator. You have to, remember I talked about a moderator? It was paraffin, it was graphite, it was water. They didn't know what moderator to use to slow the neutrons down. And they took a guy, his name was Botha. He's a Nobel Prize winning chemist, and they said, we want you to tell us what we need from moderators. And again, this guy is really good. And he creates an experiment, and he's using graphite as a moderator, and it doesn't work. It's terrible. It will not work. And he's doing all these things, and he decides, he determines, you have to use heavy water. Heavy water is expensive, it's rare, and that just pushed their atomic bomb project back a long ways, because getting enough heavy water for a reactor, they were going to have to get it from Norway. I mean, this stuff is hard to get. There are two theories on this, on why the graphite didn't work. One is both the thought giving the atomic bomb to Adolf Hitler is not a good idea. He's destroying enough of the world. If we give him this, he'll destroy the rest of it. He sabotaged the results. Now, nobody knows because both is dead, but the other one, which is probably more plausible, and this is a problem that we had years before, and this is something Leo Szilard worked on and fixed and solved, is there's boron, naturally boron in graphite. And boron sucks up neutrons. It will stop your reaction. And Szilard learned that if you bake the graphite to like 400 degrees, it bakes the boron out of it. And they had to do this for all the graphite blocks that they had that they put in these reactors. Botha didn't do that. He didn't know about the boron. And the boron was sabotaging his results. The other issue is when you look at the size of the stuff that we had to build, the gaseous diffusion and the reactors, where are you going to get 20,000 workers from to build this stuff? Where are you going to get the structural steel? Germany's in a war. If there's any steel laying around, it's going to go into a tank. Saying we need 390 tons of structural steel to build this building to do gaseous diffusion. And if you start building 43 acres under one roof, we're going to bomb it. Right? World War II, the United States, we're going to bomb it. So all of these things conspired against Germany to have an atomic bomb project. So when the war was over, like I said, Grove sent these guys to follow the troops into Germany to find out what was going on with the German atomic bomb project. It was essentially dead. It had been dead for a long time because they did not have the men, they did not have the materials to make the stuff, to make the buildings to do gaseous diffusion or to make plutonium. It was not going to happen. Does that make sense?
I think we're getting beat up, Bob, but thank you very much for the talk. That was really great.
Thank you. Thank you for coming. I appreciate it. Yes. I wanted people to. I'll sell this to you. You know, it's cookie dough.
Chocolate chip.